Hi. Whoever's giving a talk, it will be helpful if you can put up your presentation, please, on the Indico page.
We just send an email. Oscar, could you please upload your talk?
Yes. Can you hear me?
Yeah.
Yes.
Okay, I will upload it.
Thank you.
I think you should see already the talk. This is Oscar.
Okay, thank you very much.
You're welcome.
Thank you.
Óscar, could you please share your slides?
Yes. Okay, can you see the slides?
Yes. Perfect.
And also the mouse, right?
Yeah.
Okay, great.
Okay, maybe we can start. So welcome everyone to the first parallel session of the Working Group 2. We will start with Óscar Boente García and talk about recent results from heavy ion collisions at LHCb. Óscar, you will have 15 minutes. I will give you a warning at 12, and then there will be 3 minutes of questions and discussions. You can start.
Okay. Okay, thank you. So today I will give an overview on recent results from heavy ion collisions at LHCb. So this is a scheme of the LHCb detector for round 1 and round 2. So it's a one-arm spectrometer at LHC, fully instrumented between 2 to 5 units of pseudo rapidity. In particular, we have a tracking system with good momentum resolution, excellent hadron and muon ID, precise vertexing, calorimeters, and also this Herschel detector, which is located meters away from the interaction point, and is used to beat a background from UPC collisions, measuring the high rapidity region. So as you see in this scheme here, we are the only detector at LHC that covers this acceptance with all the detector systems. So this can be very well exploited in heavy ion collisions. And in particular, today I will talk about proton-led collisions and lead-led collisions. And here you have the different data sets that we have. We had 2 data takings from each of these systems. And the last ones have much larger statistics. And also in proton-led collisions, we take data in 2 configurations, one with a proton going towards the detector, which was the forward configuration, and then also in the backward. So we can prove a very large region of pseudo rapidity. So this is what I will mention today. I will start with a new result on charged particle production in proton-led collisions and proton-proton collisions at 5 TeV. Then I will follow with production of Chi-2 and Chi-1 states in proton-led collisions. And then another very recent result of photo-produced J-psi in peripheral collisions in lead-led collisions. And finally, coherent J-psi production in lead-led collisions, but now in ultra-peripheral collisions. So prompt charged particle production is usually a proof of the initial state of the collision. And the particular thing of LHCb is that we can go to an unprecedented range in X. So you have this in this scheme here. We can go to this red region of very low X. And this allows us to potentially probe the saturation region at higher PT than the rest of the experiments. And then we also have, with the backward configuration, the violet region here, where we can compare with results from RIC experiments like Phoenix in gold proton collisions and Brand's results. So what we want to measure is the nuclear modification factor, which is the ratio of cross sections in proton-led over proton-proton collisions. So we have measured these double differential cross sections of charged particle prone charged particles in proton-proton and proton-lead collisions at 5 dB. So here you have the kinematic range and the pseudo rapidity coverage, which is slightly different in each proton-lead configuration due to the boost in the center of mass system. So basically the analysis, we measure the yields of prone charged particles with the tracking system. And then we have to apply several corrections to the raw yield, mainly the reconstruction and selection efficiencies, and the background which comes from fake tracks and secondary particles. So you have here the results of all these cross-sections in all the bins. The proton-proton result is scaled by the lead mass number for comparison. And here you can see the final uncertainties, which go down to 2.8 in the cross-section and down to 4.2 in the RPPV. But they are bin dependent, and you can see here the different contributions. So this is the result for the nuclear modification factor. So on top you have the result in the forward region, and in the bottom plot you have the result in the backward. So in the forward region we see a suppression for all the bits, but it's stronger with more forward rapidity and at low PT. And in the backward, we see a suppression for low PT, but enhancement appears for PT larger than 1.5, similarly as it happens in rig experiments like Phoenix in backward region. So we compare these results with different models. The green model is a EPPS calculation, which is compatible in the forward region with our result, but doesn't reproduce the enhancement in the backward region. And then we have a color glass condensate calculation, which is in violet and reproduces the RPP for high PT, but overestimates the RPPV for lower PT. Sorry. And then we have this parton QCD calculation, which includes multiple scattering effects. And this seems to work for high PT in the last bin, as it did in the Phoenix result, but it doesn't reproduce the shape in the other bins. Okay, so here on top you have another comparison for different bins in pseudo rapidity and also the ALICE result. And you see there is a nice continuity between the different results, between the different acceptance. And another interesting thing is that the enhancement starts at different PT value, at different PTs for different pseudo rapidity values. And finally, we did this study using these auxiliary variables, X and Q squared experimental, which are defined like here. And the idea is to see indirectly the evolution of the RPPV with X and Q square partonic variables. So we plot this for a specific range of Q square experimental, and we took the values for the forward, the backward, and the results from ALICE and CMS. And you see that there is this nice continuity between the results for the different Q square bins and between the different regions of the space. Okay, so the next study is a prompt production cross-section ratio of the Chi-C states in proton lead. And this is the first measurement of these states in nuclear collisions at the LHC. So this complements the measurements of other Marconian states in proton lead collisions. And we do this by measuring with the decay to a J psi and a photon. And we have two strategies to detect this photon. But first, the prompt candidates, we select this with this TZ variable, which is called the pseudo proper time, and uses the information of the decay vertex and the primary vertex of the event. So the two strategies that I mentioned are using converted photons, which are photons converting with the material. This gives us excellent mass resolution, but statistics. And then using the calorimeter, which gives us better statistics, but worse resolution. And this is what we measured, this ratio of cross sections, which has the advantage that most of the efficiencies get cancelled. And we see that the ratio is compatible with unity for the both methods, and we don't see rapidity dependence either. And then we compare with this proton-proton result, and we see that the calorimetric sample result deviates, well, is consistent within 2 sigma with the result, which, if there is no energy dependence in the nuclear effects, would mean that they affect similarly to both states. Okay, so moving to lead-lead collisions, I start with peripheral collisions, so both lead nuclei do not fully overlap, but there is some overlap between them. And here we want to study the coherently photoproduced J-psi because one of the motivations is this low PT excess observed by other experiments, which could have this production mechanism as origin. So we use the 2000, and this is the first lead-lead measurement at LHCb. We use this 2018 sample, and we covered these centrality ranges here, and the centrality is determined with a study of the equal energy, the electromagnetic calorimeter, and a Glauber calculation. As before, we select non-prompt prompt J-psi by this pseudo-proper time selection. And we get the J-psi signal by a fit to the J-psi mass, and then the coherent contribution is extracted with a fit to the log PT square, the distribution, to separate the coherent J-psi from the hadronically produced J-psi. So you see that the coherent J-psi has very low PT. And afterwards, we calculate the yields of J-psi by introducing the detection efficiencies. And we measure the yields in PT, rapidity, and centrality beams. So as you can see here in these 3 plots. So the PT shape in particular is the most precise PT dependent measurement to date of this photoproduced J-psi. And you can see that the model qualitatively reproduces well the result, although there seems to be some scale factor. And we can confirm that this photoproduced J-psi is the source of the excess seen in the lead-lead collisions. Okay, so this is the last result. It's a preliminary result of a coherent J-psi production in ultraperipheral collisions of lead-lead nuclei. So here there is no overlap between the nuclei, and we select this kind of events requiring minimal activity in the calorimeters. So this uses the small 2015 sample. So this will be improved in the future with the larger 2018 sample. And similarly as before, we get the J-psi signal with a fit, and then we get the coherent J-psi contribution with a template fit with to the log PT square distribution. So the templates I taken from Starlight. And yeah, this, and then we correct for detection efficiencies, and we measure the cross section. So in the final publication which will come out very soon, we will improve the selection with using information from the Herschel detector. So this is okay. Yeah. So this is the final result in different means of rapidity. And you can see comparison with different models. And just mention that the luminosity is the main limitation in the uncertainty for this study. So I get to the conclusions. I showed you new results from LHCb in heavy ion collisions, and you can find the full list of published results here. So we show the first determination of RPPB for prompt charged particles in the forward and backward regions at LHC. So we measured the prompt charged particle production cross sections in proton-proton and proton-lead in 5 TeV at 5 TeV. And the uncertainties we obtain are down to 4.2 for the RPPB observable. And we hope to set strong constraints to nuclear PDFs and saturation models down to very low X. We also measure the first, for the first time, the production of Chi2 and Chi1 states in nuclear collisions at LHC. And in lead-lead collisions, we study the J-psi product, the photo-produced J-psi, both in peripheral and coherent collisions. And these are the first results of lead-lead collisions at LHCb. And we got the first, the most precise determination of the PT spectrum up to date, confirming in this way the stress as a source of the photo-produced J-psi as a source of the excess. So that's all I have. Thank you very much.
Well, thank you very much, Óscar, for this nice talk. And we have actually quite a bit of time for questions or comments. If you have any comments, please go ahead. Well, okay, I don't see any questions or comments. Well, so let me thank you again, Óscar, and we can move to the next talk. So the next talk will be a theory talk from Tomasz Stebel. He will talk about prompt photon production in PP scattering and high energy factorization. So Óscar, if you could just stop sharing your screen so that Thomas can share.
Hi, do you see the slides?
Not yet.
Let me see. Okay. Let me what screen? Maybe now?
Yes, now we can see, but can you make?
Okay. Okay, so sorry. Okay, so do you see it now?
Yeah, now it looks perfect. Okay, Tomasz. So
okay.
You have 15 minutes, and then there will be 3 minutes of questions and discussions. I will give you a heads up after 12 minutes. You can start now.
Okay, thank you very much. So thank you very much for the organizers for giving me opportunity to talk about this project. So I'll be talking about photon production in PP scattering, and this work was done with Krzysztof Golec-Biernat and Leszek Motyka. So, okay, so let's start with the process which I have in mind. So we have scattering of 2 protons at a very high energy. And then at the final state, we have isolated photon measured, which is isolated from hadronic state. So just for the notation, I have so I denote the photon for momentum as Q. So now let's move to the partonic cross section. So at partonic level, this process is the following. So if we are in the collinear factorization framework and want to look at the photon with non-zero transverse momentum, then the leading order parton channels are quark-gluon and quark-quark channels, and the next to leading order also the gluon-gluon channel enters, and of course some higher corrections. So this is of course the collinear factorization. If we are at high energy approximation, high energy limit, and we consider KT factorization, then so the energies in the center of mass are much larger than other scales. Then we are in the small x regime, and the gluon distribution is dominant. So those 2 diagrams would be dominant. So because of the gluons at initial states. Okay, so let's start with this first diagram, this leading order diagram, which we calculate in the so-called hybrid factorization. So the quarks are collinear to the proton, and the gluon is off shell and has non-zero transverse momentum kT. So now the cross section for such a process is a convolution of transverse moment of standard collinear distributions of quarks, the unintegrated gluon distributions, UPDFs, which I denote by F, which describes this emission of gluon, and the hard part, which is here. So it's important to stress that here we have sum over all quarks. So we have all flavors except top, of course, and both C and valence quarks are entering. Okay, so now let's move to the second graph. So the gluon G star contribution. So the star means that the gluon is off shell. So here we have two off shell gluons with transverse momentum. Both has non-zero transverse momentum, and the cross section for such a contribution is as a convolution of transverse momentum dependent distributions, UPDFs, for both protons and the hard part H, and which is a sum over 8 diagrams. These are 2 to 3 diagrams, which can be computed perturbatively using the Lipatov vertex. So now, in order to combine those two channels, we have to make sure that we have no double counting, and so when you look at this diagram G star, you can think of this as in the KT factorization framework. You can look at this as a splitting of the gluon into quark anti-quark, and then the scattering of the quark on the gluon, the second gluon. So this G star contribution contains also a part of this leading order contribution, namely the part which contains C quarks. So in order to combine G star with Q G star, we need only add to G star contribution from Q valence and G star. So this approach, in fact, this, let's say, next to leading order approach is sum over G star and Q valence, so two contributions. And this Q valence is the same calculated as before. Okay, so one thing which we need also is unintegrated gluon distributions in both channels. So these are the non-perturbative quantities, and some models are needed for this. So we shall use 3 models very popular in the literature, namely, first is Goles, Bernard, and Wooshoff model, the most simple you can imagine, probably. And this is a model fitted to data at very small x. It contains saturation. So there's a Gaussian in KT, has shape of Gauss, and this is the original one, this part, and in order to kind of extend it to higher x, we modify it by the factor 1 minus x to power 7, just because we have also data which have larger x's. but okay, you'll see how it works. And next is this UPDF is the solution of CCFM equation, and we use the solution available in the literature, and this is solution by Jung and Hanson, and later also Jung and Hauptmann provide the solutions of CCFM. And finally, we're using the Kimber-Martin-Riskin prescription, which is based only on basically a differentiation of the collinear PDF. Okay, so with some small details, but okay, so let's have a look how those 3 or 4 distribution looks like. So first of all, the GBW is very narrow in KT. It has strong cutoff above 1 GV. So these are two X values which are interesting for us, and so GBW has strong cutoff at KT greater than 1. The KMR has long tail 1 over KT squared in the the whole range of for large KT. It has 1 over KT squared, and the Jung, Hanson, and Hauptmann are kind of in between those 3 gluons. So we have 3 gluons which have quite different behavior, and you can look also at compare those to the standard collinear PDFs using this approximate formula, which says that when you integrate the UPDF over the KT squared, then you get the standard collinear PDF. So at these plots, you have the black dashed dot line is the collinear PDF, and the camera is the green line, which is very close to the collinear PDF, and there's so the GBW has different shape in X actually, and then the collinear PDF, and the Jung Hanson has different. So it's very similar shape, but there's a kind of constant factor which difference between those 2, between integral and the PDF. Okay, so now let's have a look at data which we are using. So I will show 3 sets of data. So this is Atlas 7 TV, CMS 7 TV, and Atlas 8 TV. And these are sets which have low QT data inside, and the especially this Atlas 8 TV is interesting since it has, as you will see, small errors and a very broad range of QT from 20 GeV up to 1500 GeV. Okay, so in this thanks to that, we have like we are dealing with X's which are 0.002 to 0.2. Okay, so now here's the results for quark gluon approach. So the first, so columns are different experiments. You have Atlas 7 TV, CMS 7 TV, and Atlas 8 TV. At rows, you have different rapidities, so growing rapidity going down. And so let's focus on this Atlas 8 TV, which is has the smallest errors. So first of all, this is theory to data plot, so very sensitive to any difference. And as you see, that the errors are very small. Experimental errors are very small. So these are so let's look at the KMR, which is this green band. You see that this is below the data like 20%, but it's the ratio is very stable. It's basically from 20 GeV up to like 600 or something GeV, it's flat. So we have like 20% difference, which is very good for this simple model. And at high QT, you have you're at large X. So this approach is not very suitable for this. But as you see,
you have 3 more minutes.
Yes, thank you. Okay, so when the GBW has completely different shape in the end in the QT, which is okay. It's a very simple model for small axis applicable, and the Jung-Hanson has good description of data at low QT, and at high QT you cannot basically use it because it's not constrained for such high QT. So it's only for QT smaller than 100 GeV. Okay, and you see one interesting feature is that here we are below the data, which is something which you can compare to this integral, where for the integral the UPDFs are above the collinear PDF, which kind of suggests that you're not really in this process of photon production, you're not you're not sensitive to the overall normalization of your TMD gluon PDF, but you're sensitive to its shape. So this is basically you're measuring this shape of UPDFs. Okay, and so the second approach, this more complicated like NLO approach is here the same data sets, and as you see here the description of data is worse. You at mid QT you have like 40% difference, but at very small QT where there's, let's say, in the small X regime you have good description of data and basically almost all both three PDFs. So but this basically suggests here you're below the result for quark gluon. So you see that there's so this G star is smaller than Q star Q G star. Okay, so summarizing, so we calculate the cross section for prompt photon production using KT factorization framework. We have tested 3 well-known transverse momentum dependent gluon distributions, and we had quite good description of data, especially for those QG star even at relative high QT, which is kind of a nice feature. And this G star channel is kind of doesn't improve the description, and it is below the QG star approach. Okay, thank you very much for attention.
Oh, thank you, Tomasz, for being on time and this very nice talk. We have a question. Farid, you can unmute yourself and ask your question.
Yes. Yeah. Hi, Tomasz. It's very nice talk. I just have one curiosity. So if you go to your slide 3, where you show the diagrams, right? So you're interested in isolated photon. Yes. How do you impose the isolation from the quark in this case? Like in your right.
So there's of course the isolation is kind of tricky because you have the in the experiments you have like isolation on the hadrons. So we had to like kind of impose the isolation on the partons, and this is based on like you kind of isolate, like you cut the cone. So there's like I think it's, I forgot the paper which is which basically describe how there's the like let's say in literature is a consensus how to do it for the hadrons, and based on this we choose the isolation cut for the partons on the partonic level, and this doesn't change so much, I would say. Okay, you can kind of play a bit.
I see, because in the formula that you show on your next slide, it looked to me as if it was more inclusive photon, right?
Yeah, yeah. So yeah, so okay. So here there should be some theta, because there would be like infinities here, but there should be some theta which impose the cuts. And
okay, thanks.
There, of course, there. Okay.
Okay, thank you very much, Tomasz. If there are no more questions, let's continue with the next talk. That will be.
So thank you very much. I'll stop sharing.
Thanks, Tomasz. Federico, can you share your screen? So our next speaker is Federico Deganutti, and Federico will talk about tank jets, techniques to leading order, and apparently the breaking of the high energy factorization. Okay, Federico, you have 15 minutes. I will give you a heads up after 12. You can start.
Okay, so today I'm going to show you the first results of a phenomenology analysis and next to leading order for this Mueller-Tang jet process, including an next to leading correction to the impact factors, which leads to this high energy factorization breaking, and I will say later what I mean by that. So after a brief introduction of BFKL and the high energy limit of QCD, comparing it to another limit of QCD, the DGLAP approach, I will introduce you to the details of this observable that are linked to this high energy factorization breaking, and then I'll show some of the measurements that have been dedicated to this observable in the past. On one hand, trying to motivate that the BFKL certainly has something to say about this, but on the other hand, the status of the theoretical prediction is quite unsatisfactory. And then finally, I will show some preliminary results, which unfortunately I compare it only to the leading order corrections. I cannot compare it to the experiments, because for that I will need to embed my findings into a Monte Carlo generator. So although no one really doubts that BFKL should be there as it is a consequence of perturbative QCD, I have to say that the search for a clear BFKL signature has been quite problematic. However, there are hints of it, especially in the context of the PDFs. However, the importance of BFKL is much broader than that, as it has to do with the high energy limit of QCD. And for instance, can be explored at the hadron colliders as the center of mass energy becomes larger and larger compared to the exchange momentum. So you can draw a parallel between the small x growth of the PDFs with the evolution toward the large rapidities for these jet observables. So when these two hard scales, S and T, becomes highly unbalanced, then you have to rearrange the whole perturbation theory for following a new hierarchy, because this log S tends to compensate for the suppression coming for decoupling, and so you have to define what's called the leading log approximation, where you include all the diagrams with the same power of alpha and log S, and likewise you can define next to leading log approximation when you include all the diagram of these logarithms. Here on the right hand side, I'm showing the typical gluon ladder that needs to be resummed to complete the leading order BFKL, together with constraint on the phase space here, so that the T-channel gluons must be strongly ordered in rapidity, while the transverse momentum must be roughly of the same order, which looks quite complementary to this other limit of QCD DGLAP, but however, they can overlap quite a bit, and this is ultimately one of the reasons why it hasn't been easy to find a clear-cut BFKL evidence. There are other mechanisms also that tend to overshadow the BFKL contributions. So that said, one way to resum these diagrams is to solve an iterative equation, the BFKL equation, given in terms of this gluon green function, which has the peculiar property of rising with power of the center of mass energy S, and is a universal probe-independent object. So in the general case, it's given in terms of its eigenfunctions, which in turn is given in terms of this Gauss hypergeometric function, which can be quite demanding to be computed numerically, especially for the phase space that's needed for this observable. And for instance, you have round-off problems so that you need much higher precision than the double or quadruple precision even. Another ingredient of the BFKL description are the impact factors, which convoluted together with the gluon green function gives you the differential cross-sections. This leads to very highly dimensional integrations that needs to be done in general, and in our case, numerically. But it turns out that if you exclude the next leading correction to the impact factors, then you can solve these multiple convolution numerically, and you also don't have anymore the problem with this Gauss hypergeometric function if you only consider leading order impact factors. So that's what this is just to show what are the difficulties for this analysis. This is for the definition of this observable. So this is a very exclusive process where you tag two jets far apart in rapidity, and you ask for a gap completely devoid of any particles in between. The requirement of a gap is to enhance color-singlet exchange signature, which will be the BFKL signature. And this is also because at the high energy, the color-singlet is predicted to be dominant. At the experimental level, the definition of the observable is slightly different in the sense that you have to cope, of course, with the limitation of the experiment. So, for instance, the gap is fixed into the central rapidity region, and also there is a finite threshold, which is pretty low, 0.2 GeV, below which any particles can be anywhere, also into the gap region. Here on the left-hand side, I'm showing the CMS 70eV analysis, where they consider the charged particle multiplicity into the gap region. There is a clear excess of events for the 0th bin, so 0 particle in the gap region, both for the data and for the Herwig 6 predictions, of which both larger, like an order of magnitude larger than the Pythia predictions. So this seems to suggest that BFKL goes in the right direction, as it is included by Herwig 6 and not in Pythia 6 predictions. On the right-hand side, this is a comparison between the BFKL predictions, a leading order, and also including part of the next leading corrections only to the gluon green function, and the D0 data. And I would say there is a good to fair agreement with the data. Keeping in mind that there is also an overall normalization that is fixed by hand. This is called gap survival probability, and is needed for compensating for some soft rescattering effects that otherwise will need to destroy the gap. Fast forward to the very recent 13TV analysis that my colleague Baldenegro will talk about in more details in the next talk. We can see that the pure BFKL theoretical prediction that is labeled here as RMK, the red band, reproduces the data very poorly. So there is certainly something missing. here on the right hand side, there is this very puzzling, I would say, rise of this color-singlet fraction for azimuthal angle. When the azimuthal angle is getting difference is getting smaller, this is really completely unexpected. The color-singlet fraction is basically the number of jet-gap-jet events divided by the number of inclusive dijet events. So our idea was to complete the next leading analysis to see if we could get anything better. So, but before going to see the detail, some of these results, I will allow me to open a parenthesis trying to explain what I mean by this high energy factorization. So as we took these expressions that were published by this collaboration here in Madrid for these next leading impact factors, we discovered that as we try to conform the observable definition to the actual definition that is used at the experimental level, we discovered that there are some log S factor that are left out from the gluon function, and they can only be left into the next leading impact factors, which is really unexpected, and in some sense is perhaps from a theoretical point of view is certainly some problem, because it is somehow telling you that your next to leading impact factors as a leading component because of this log S enhancement. And this comes from the observable definition, because as you know, if you imagine, for example, you have one quark that becomes the jet, and then this other gluon that if it is emitted with a PT lower than the calorimeter threshold, then it can be emitted everywhere, also in the central rapidity region. So you have to integrate over it, but one would expect this configuration to be suppressed in BFKL, as it is usually also for other observables, but in this case it's not. It is actually enhanced by this log S factor or rapidity. And we actually checked their calculation, so unfortunately there is no simple mistake so this is how it is, and perhaps the way the observable is defined, or perhaps there is some other problem behind. So here I'm showing a pure leading order comparison between gluon-induced and quark-induced cross-section for difference in rapidity and the PT of the jets. So the gluonic part is normalized with this factor so that the different profiles are due only at this leading order to the different PDFs, and it's showing why the gluonic part is dominating at small x. And here is are the very preliminary results that we have at next leading order. So the same plot, we see that the gluonic part seems to be even more enhanced compared to the quark components. There is clearly something, some pathological behavior that is happening at rapidity equal to 6, where the cross-section leading order plus next leading order is becoming negative, which of course doesn't make sense. But in some sense, it could be expected in the sense that BFKL correction and next leading order are often very large and very negative. In the history, many solutions have been tried, not for this observable, but in general to tame the next leading corrections of for BFKL, which include this BLM way of setting an optimal renormalization scale, which in this context usually turns out to be a much higher renormalization scale than the natural one that we used, so they would reduce the size of the next leading components. There could be also another effect that is certainly has to do with this high energy factorization and breaking, and is the fact that when you impose a gap, then you end up having other additional logarithms that they need. They're part of the resummation. That we didn't do it, so perhaps including that resummation would fix this issue of the negative cross-section. Here, allow me to say just one last thing. For this plot of the cross-section as a function of the azimuthal difference between the jets. So there are very few points here, but this already can be seen that that very puzzling rise toward the small azimuthal difference cannot be explained by only including next to leading impact factors into this description. Finally, another possibility is to modify the observable definition, preventing the emission into the gap region instead of fixing the gap as it is right now in the experiment, imposing an invariant mass, an upper bound on the invariant mass for each impact factors. So I will stop here while you can look at the conclusions. I think.
Oh, thank you very much, Federico. You're right on time.
Yeah.
Okay, if there are any questions or comments, please, we have 2 more minutes. Yes, Reno, please go ahead.
Hi. So thank you for this talk. I do have a question, because the problem of the negativity of cross sections at next to leading log for small x physics, be it BFKL or BK, has been long known. I mean, we're still struggling with how to fix it, but there are quite a few assumptions on where it comes from and how we could fix it in principle, even though in practice it's complicated. So did you look into that, or because you can find thousands of papers on the topic?
So you're saying about that the sum of leading order plus next to leading order becomes negative? Is it to be expected? Or well, it's just the leading order, the next to leading order correction? Because those are completely negative, of course. Usually, when you sum the leading order part to the next to leading order part, as this should be something that measurable, you don't want to get a negative cross-section. It's not. It has happened already, and
yeah, we still have trouble solving the whole next to leading log evolution equation, of course. But in principle, we know that there's a collinear corner of phase space, which is tough to deal with in usual resummation schemes for small x.
Yeah.
So there have been many suggestions on how to fix that. So I'm simply asking, did you look into those, or? Because you're saying
yes,
factorization breaks, which is a strong statement here.
Yeah, so the statement, I don't know, I mean by factorization breaking that there is this log s that ends up into, in a way that's unavoidable into the next leading impact factors. The resummation, I think, for the collinear resummation you're thinking about, ends up into the gluon-green function, if I understand correctly what your remarks. And this, and I am familiar with that, and it has been used to tame, or let's say to borrow some of the DGLAP-like contributions and add them to the BFKL contributions. But that is, I would say, is literally, is not exactly on the point, because that is already included in into the gluon-green function. The gluon-green function next to leading order here, I'm using like, I'm using in an heuristic way the next to leading eigenvalues with the leading order eigenfunctions, which I mean, of course, is not correct, but since we cannot resum the next to leading order non-forward BFKL equation, I didn't know any better. But this is for the next leading impact factors. I think it's a slightly different issue.
Okay, thank you.
We have another question from Raju. Raju, please go ahead.
Hi. Yes. Can you please go to the slide where you showed the comparison with the CMS data? So this one here. So what's very striking is that you see that the rapidity dependence is totally off, right? And so what's all this MPI plus SCI that kind of completely switches the dependence?
Yeah, so this is related to that gap survival probability I was talking about, and is due to these are models that model soft physics interaction. Actually, I think you're lucky because the next speaker is the author of this analysis by CMS. So I'm sure he know to answer your question better than I do. But anyway, these are models that include soft rescattering and anyway, soft physics remodeling.
I see. So because that really qualitatively changes the behavior, right? Of the
yes, yeah. I mean, this is usually the gap survival probability allowed you to just shift the whole prediction on the y-axis, like a fixed, constant normalization. But with those modeling, they predicted some rapidity dependence for this soft rescattering. But I don't know exactly what's the soft process that would lead to that.
I mean, do you think that going beyond the LO impact factors could qualitatively change this?
I would say not really. I mean, what's really striking is this, except for the delta phi, this steep rise, I would say, for small delta phi. I think that to have that, you need like many emissions, not just one more emission. Because with next to next, you will get one more emission from the impact factors, and no emission from the gluon function in this context, because that's elastic.
Okay, thank you very much.
You're welcome.
We have another question from Martin. Martin, if it is a quick question, please go ahead. If not, I would suggest to move it for offline discussion.
Sure. No, it's just a very quick comment to this remark that there's a violation of energy factorization. So I think what we see here is not really a violation of factorization. The problem, I mean, we discussed this already offline before, but the problem here is that you allow for emission into the gap region. And because you do that, you go beyond the initial calculation, which just assumed you don't have this kind of emissions into the gap region. So to take this into account in general, we have to include the complete 4H gluon state, which of course with all possible color correlations and whatever, which of course on top is far more complicated. But I think the problem is not a conceptual one that we see here, breakdown of energy factorization. It is more you extend sort of the calculation which was meant for the gap to be empty to the case when you allow soft emission into the gap, which of course is experimentally very, very motivated. But that's the reason why you have this kind of problems. If one could extend the calculation, I think conceptually there should be no problem here, as far as I understand.
Yeah, so thank you for these remarks. So the way I see it is that it's true that when you do this calculation in the high energy limit, you make some assumption, like for instance that your partner is very forward. But usually what happens is that when you have your final expression, then you realize that as you try to move into like the prohibited backward region, naturally you will get a suppression, or you will get a component that it doesn't its size is negligible. But in our case, it's not like that. It's actually, you have this enhancement that is certainly is connected to this double logarithms that you have for when you impose a gap in the central rapidity region. But it's still, in some sense, I would say, unexpected that you don't get, for example, a negligible contributions when this gluon becomes increasingly central, but actually you get some sort of enhancement for that. And yes, I mean, I'm not saying that we completely understand everything about this high energy factorization and how to solve it. Yeah, I don't have any better answer for now.
Oh, Federico, thank you very much for this nice talk. We are really falling behind the schedule, so let's continue with the next talk, Cristian Baldenegro. So
yes,
stop sharing your slides.
Yes.
All right.
Okay.
So
the usual thing, Cristian. So it will be 15 minutes. I will give you a heads up after 12.
okay, thank you very much, and it is a pleasure to talk with you about this recent measurement by a joint effort between the CMS and TOTEM collaborations on hard color singlet exchange in dijet events in proton-proton collisions, which is a study that we recently submitted for publication to PRD just a few months ago. And here, just to give a brief outline of the talk. So first, I'll talk about the relevant detector components from CMS and TOTEM important for this analysis. Then I'll recall the process that we're interested in, which is what Federico was talking about, the Jacob-Jet process as a probe of BFKL dynamics. Then I split the talk in two parts. One of them discusses the study of Jacob-Jet events in proton-proton collisions, relying only on the CMS detector for the jets. And then I'll discuss when, in addition, we detect the presence, we detect an interproton with the TOTEM Raman pod detectors. And I will conclude with some remarks at the end in the summary. So for this analysis, we rely on the CMS detector, and we use the full, which is a general purpose detector at the LHC. And with CMS, we can reconstruct charged particle tracks at central pseudo-rapidities, and also it's equipped with a system of calorimeters covering an acceptance up to 5.2 units in pseudo-rapidity symmetrically. And this translates to an acceptance for the jet reconstruction for jets of pseudo-rapidity of up to 4.7 units. And for the TOTEM part of the analysis, what we're using is the Raman pod detectors, which is this system of forward tracking detectors in order to measure these interprotons that remain intact as a result of color singlet exchange of the proton. And they're scattered very small angles with respect to the beam, and they lose a small fraction of their original beam momentum. And then the idea is that you can simultaneously have a signature into CMS detectors such as jets, and also detect these interprotons with the TOTEM Raman pod detectors. So the physics target, the behavior that we're trying to understand is the high energy limit of QCD. So the limit where the central mass energy is much larger than any other scale. And as Federico was telling us earlier, in this limit, the fixed order perturbative QCD approach breaks down, and you have to take into account these logarithmic enhancements of the strong coupling constant to all orders in alpha S by doing this resummation of large logarithms of energy to orders in alpha S with the Valitsky, Kuraev, Lipatov, or BFKL evolution equations of perturbative QCD. And these enhancements come from these multi-gluon ladder diagrams that contribute significantly to the cross-section in the high energy limit. So this is a very important test of QCD, and it's something that is very challenging to isolate experimentally. So the process that I'm interested in studying is the production of two jets separated by an interval in pseudo-rapidity that is void of particle production. And this signature is expected from a hard color-singlet exchange in the T channel, which in perturbative QCD is a two-gluon exchange in a color-singlet configuration. And more importantly, in the high energy limit of QCD, so when these two jets are largely separated in rapidity, this should correspond to perturbative permanent exchange or BFKL permanent exchange. And also very interestingly, since we're asking for a pseudo-rapidity gap, then other high order corrections in QCD, such as those given by big lap evolution, for example, are strongly suppressed. And this is because in the calculation, you need to introduce a Sudakov form factor to account for the suppression of radiation in central rapidities. And there are a lot of more details about the theoretical calculation, as Federico was mentioning in his talk. And now we have a mechanism at short distances for this gap formation, but also you can have the presence of soft parton activity that can destroy the central gap signature between the jets. And this is usually parameterized by means of gap survival probability, which is a non-perturbative quantity, which is very difficult to understand theoretically. So in a second part of this study, we're looking at the jet gap jet signature, but in addition, with the presence of an interproton detected with the TOTEM Raman detectors. And since the proton remains intact, you reduce this spectator or parton activity. So the central gap signature between the jets should be more likely to survive. So this is something that I'll address in the second part of the talk. So I'll turn now to the CMS measurement. So this is based on 13 TV data at very low pileup. We had mostly single proton-proton collisions per bunch crossing. And whereas in particle flow jets, jets with a radius of 0.4. And for the selection requirements, the two highest PT jets have a PT of at least 40 GeV for each of them. And these two leading PT jets, they have a minimum sort of rapidity of 1.4 units, and they go up to detector acceptance, so up to 4.7. And they have opposite sign sort of rapidities. They are on opposite hemispheres of the detector. And this is to favor the T channel color-singlet exchange topology. And the pseudo-rapidity gap between the jets is defined by means of the charged particle multiplicity between the jets, where each of these charged particle tracks is between -1 and 1 units in pseudo-rapidity and has a minimum PT of 200 MeV. And now, just because you can ask for a pseudo-rapidity gap, it doesn't mean that you're free from background contributions. And the main background that we have in this analysis is the fluctuations from a color exchange Dijet event. So for example, you can have single gluon T-channel exchange for Dijet production, and which usually populates the high particle multiplicity when you count the number of particles between the jets. But you can have fluctuations from this color exchange background that will resemble the signature that we're actually interested in. So this is something very important that needs to be modeled. So here, what I'm showing here in these plots is the number of charged particle tracks in the central pseudo-rapidities between the jets. And here, what we're looking at on the left-hand side is one way to estimate this color exchange background, which is by defining a control Dijet sample, which is this blue histogram, where for the blue histogram, the two jets are on the same hemispheres of the detector, so they have the same sign in pseudo-rapidity. And this sample, this orthogonal Dijet sample is enriched in color exchange Dijet events. So you can use it as a database sample of color exchange contributions, and you normalize it at high multiplicities. And you see here very clearly when you go to very low multiplicities that you have an excess of events from the nominal data sample, which is these black data points in the first few multiplicity bins. And then the background expectations predict a completely different trend. So these are the signal color-singlet exchange events that we're interested in. And the other method consists on simply fitting the particle multiplicity distribution with a negative binomial distribution function at high multiplicities, and then you extrapolate it down to the lowest multiplicity events. And then you again see this excess of events, which is the color singlet exchange signal events that we're interested in. And the main observable that we extract in this measurement is the fraction of the ratio of the color singlet exchange Dijet events divided by the total number of Dijet events. And this variable, we can extract it as a number of various kinematic variables. So for example, the delta eta between the highest PT jets, the second jet transverse momentum, and delta phi between the highest PT jets. And here what we have are the results from this study. And on the y-axis, we have the color singlet exchange fraction FCSE as a function of delta eta between the jets, where we see that there's a clear dependence. So when you go, so this fraction grows when you go to larger and larger delta eta separation between the jets. And here it's as a function of the second jet and transverse momentum, where we see that there is not a strong dependence. So it's mostly uniform as a function of the second jet and transverse momentum. And as a function of delta pi, we see that the color singlet exchange fraction maximizes when you go to the back-to-back configuration. So for when delta pi is close to pi, and then it approaches a constant value when you go to more narrower and narrower delta phi separations. And then we make comparison with two theory calculations. And based on BFKL next to linear log resumation with leading order impact factors, and by two theory groups. So the RMK prediction is in red, and then the EEIM prediction, which comes with two sets of curves, is represented by the magenta and the yellowish curve. So, the magenta curve, it accounts for a event by event simulation of the gap probability with multi-particle interactions, and the yellowish curve accounts for it when, in addition, you put soft color interactions or SCSI. So something that we noticed that is very challenging to describe theoretically the measurement, all aspects of the measurement simultaneously. And here, what we have is a comparison to measurements at lower collision energies. So comparing to measurements by the CDF and D0 measurements, and also previous measurement by CMS and 7TV. And something that was noted is that when you go to lower collision energies to higher collision energies, this color singlet exchange fraction decreases when you go from lower to higher square root of S. But something that we note here with the 13 TeV measurement is that our measurement at 13 TeV compared with the one at 7 TeV, they are compatible with each other within 30 centimeters. And so, which can be seen as a signature that at the LHC energies for the jet process, the gap probability stops decreasing for this process. And here, this is a comparison of the measurement by CMS at 13 TeV compared with the previous measurement at 7 TeV. And here, this is just to stress that with the current measurement at 13 TeV, we extend very nicely this measurement to higher values of delta eta between the jets. So it complements the phase space very nicely covered by the previous measurement at 7 TeV. Now, briefly highlight the results from the CMS TOTEM combined measurement.
Christian,
so here,
Christian,
yes.
Sorry, you have 2 more minutes, okay?
Okay, thank you. Yeah. So here we have the same Dijet as central gap definitions as with the CMS only analysis. And then there are 2 requirements of the interproton. So the fraction of the beam energy lost by the proton, psi, must be at most 0.2 or 20%. And the forward momentum transfer square at the proton vertex must be between -4 and -0.025 GeV square of the proton. And here we can also look at the number of tracks between the jets, and also do a similar treatment of the color exchange background. And by defining an orthogonal Dijet sample and also by fitting a negative binomial distribution function at high multiplicities. But with both approaches, you see that there's an axis of events at the lowest multiplicity bins, which corresponds to this signal events of Jacob-Jet events with an interproton that we're interested in, which is the first time that this kind of events are studied experimentally. And what we have here is the blue data points are the same data points that I was showing before for the CMS only measurement. And this red data point, which is obtained after integrating over all the available statistics that we had for this measurement, is the CMS and TOTEM measurement of the color-singlet exchange fraction. So what we notice here is that this color-singlet exchange fraction is larger than the one that we obtained with CMS, which can be interpreted as a consequence of a lower spectator parton activity in events with an interproton for the CMS TOTEM measurement. So to conclude here, we had a unique opportunity to study the hard color singlet exchange process at the LHC. So for the Jacob-Jet measurement of 13 TeV, what we noticed that there's the fraction of Dijet events produced by color singlet exchange is about 0.5%, and there's no further suppression between the 7 and 13 TeV results experimentally. And then for the Jacob-Jet events with interprotons, this is the first study of this process, and which points that for a possibility of doing future differential measurements in the future. And this color singlet exchange fraction for the CMS TOTEM sample is larger by a factor of about 3 plus minus 1.1 or so than in standard Jacob-Jet events. And here, just to mention, to put again the reference that this has been submitted for publication recently. Thank you very much.
Thank you very much, Christian. Thank you for being on time as well. We have 2 minutes if there are questions or comments. Please go ahead, Leszek.
Hello, Leszek Motyka. Good afternoon in Poland. So thank you, Christian, for very nice talk and analysis. And I think it's particularly exciting that you made this analysis for TOTEM, which is a different setup than the central gaps. So this is very valuable analysis. And I would like to comment on this soft co-interaction part, which Raju asked before. So I think it's pretty interesting approach, which was developed by Gunnar Ingelman mostly a long time ago. And this actually is about rescattering and core redistribution in the final state. So the dependence on PT for the gaps revival comes from the fact that there is different activity in high PT events and low PT events. So in order to get to high PT jet, we need to emit more partons, so to say. So you get denser parton state, and then there is more probability to reshuffle color between different partons, and this changes the gap survival probability. So in a sense, this is, and this also can create to some extent the gap, destroy or create. So this is pretty interesting phenomenon, and I think this is very hard to understand it from the first principles actually, but it's quite successful approach to different scattering, diffractive scattering observables. So this is basically a comment, and a big thank you for the analysis. Thank you very much.
Thank you for the remark.
Thank you very much. I would suggest, if there are not urgent questions, to move to the next talk to be on time. So thank you very much, Christian, again. So our next speaker is Farid Salazar. He will talk about forward Dijet production. So Farid, could you please share your screen? Perfect. Okay, so you have 15 minutes. I will give you a heads up after 12. You can start.
So can you hear me?
Yes.
Okay, fantastic. So thank you very much, Tolga. I want to thank the conveners and the organizers for putting this nice conference. So today, I'd like to discuss some developments on understanding Dijet and dihadron production beyond TMDs at the EIC. And this is work that I've done with my collaborators in this paper, and some work in progress also with my collaborators here. So let me start with the outline. First, I will briefly discuss semi-inclusive observables at the EIC that are interesting for accessing the small gluon X structure of nuclei. I will remind you of the TMD factorization framework, in particular the Weizsacker-Williams TMD. Then I will discuss how one can go beyond that using the CGC EFT. And in particular, I will try to briefly highlight the difference between kinematic and genuine twists. And then I will show you numerical results. And I will try to argue and explaining what kinematics one access these different types of twists. And then I will end with my summary and outlook. Okay, so let me review these two observables. The first one is the semi-inclusive production of dihadrons, forward dihadrons. By forward, I mean in the direction of the electron, or more precisely, the virtual photon. And what you see here is the back-to-back peak of these dihadrons in the azimuthal angle in transverse space. And it has been pointed out that saturation, gluon saturation, leads to a suppression in this back-to-back peak. So if you compare the black curves with the red curves, the blacks are for collisions with proton, and the red curves are collisions with nuclei. And you see this suppression. Of course, there are other mechanisms that lead to this suppression, like Sudakov, and those have to be taken into account. They have been taken into account for this particular plot that I'm showing you in this work by Elke and collaborators. But this could be a potential way to access saturation at the EIC. And just briefly like to point out that tomorrow there is going to be a talk that discusses dihadron correlations in PP and PA by Xiaoshuan. The reason why one expects this suppression is because the typical momentum transfer from the nucleus or proton to this quark anti-quark system is of order QS. So if you have a larger nucleus, you have a larger QS, you have a broadening of this back-to-back peak. Now, another observable is the production of dijets. So it's a similar process, but now the measurement is a little bit different. Now one is interested not in the angle, not in the azimuthal angle between these two jets or hadrons, but rather the azimuthal angle, the distribution of the momentum imbalance that is shown here, that is denoted as delta. So one wants to understand how this momentum imbalance is distributed. And if one looks at that observable, one can access linearly polarized Weizsacker-Williams by looking at the elliptic anisotropy of the angle between the momentum imbalance and the variable defined here as P. And as I said, it has been shown that this is proportional to this ratio of linearly polarized to unpolarized Weizsacker-Williams. And this is shown in this plot, and this is some work by Adrian Vladi and Thomas. So having these two in mind, we would like to present some progress beyond what has been shown here. So these two observables have been studied within the TMD factorization framework. But what we want to know is what are the kinematic and genuine twist corrections which are not accounted in the TMD and which are encoded in the CGC, and how large are these corrections? And do we expect them to see at the EIC? And for what kinematics? We want to quantify and answer this question. And the observables are the ones that I presented to you before. And our approach is to use the full CGC within the Gaussian approximation for the quadruple, and using the running coupling Balitsky-Kopchakov equation. And then we want to compare with the results of the TMD and the improved TMD, which I will briefly mention soon. Okay, so just to remind you of the TMD factorization. So in the TMD factorization, one assumes a separation of scales. In this case, one assumes that the momentum imbalance is very small. That means that the configuration of this jets or hadron is almost back-to-back. And then one can factorize the cross-section into a hard factor that can be calculated in perturbation theory, and a soft factor, which in this case, given that the final states have color charge, leads to the Weizsacker-Williams distribution. And this Weizsacker-Williams distribution has two pieces, this unpolarized part, which is the trace part of this distribution, and the traceless symmetric part, which is the linearly polarized part. And as I argue briefly before, one can access them in this dihadron and dijet measurements at the EIC. Now, one can go beyond this picture within the CGC, and Tuomas Lappi discussed the CGC this morning, so I will not go to it in much detail. But the idea is that now one has to resum multiple gluon interactions, and these are resummed in these Wilson lines. So now you have an effective vertices, which are denoted as this red band. And each effective vertex will come with a Wilson line. So at the level of the amplitude, you have two Wilson lines, you have a dipole. But since this is not a fully inclusive measurement, since we're interested in measuring the dihadron or dijet system, this QQ bar, then one is not only sensitive to the dipole, but one actually has to square the amplitude. One cannot take advantage of the optical theorem. And one ends up with quadrupoles as well. And this cross-section is briefly sketched at the bottom of the slide. So you have the Lycon wave functions. This is a leading order that Tuomas introduced in the morning. And then the red part is the correlators of Wilson lines, which, as I said, will include dipoles and quadrupoles. Now, this picture works within the small x, so that's why we're interested in forward dihadron dijet production. If one wants to bridge the gap between low x and small x, I think Jamal is going to give a talk this afternoon. And also the importance of non-iconal corrections are going to be discussed by Guillem's talk this afternoon as well. Okay, so these two pictures might look slightly different if you have not compared them before, but actually it was shown in the paper that is shown on the top by Fabio, Cyril, Bowen, and Feng, that one can recover the TMD approximation factorization framework from the CGC by an expansion. What one ignores are kinematic corrections, which are shown here, which are in these powers of delta over PT. And one is also ignoring, which is a little bit more subtle, genuine twist corrections, which comes in this power of QS over P. So QS is the saturation scale in this case. A framework called Improved TMD was developed not too long ago, and they show how to resum the corrections that are in powers of delta over PT. And what one shows is that they can be resummed into the hard factor. So the hard factor now depends on delta T as well. I will not discuss the details too much. Piotr and Andreas are going to elaborate on this in the talks that they have next. But what one misses in this improved TMD is this part, which are these genuine contributions, genuine twist contributions. And since the EIC has the capability to have collisions with nucleus, this might be important, this might be relevant, and they perhaps can be accessed at the EIC. Okay, so let me show you some numerical results. Before I describe these curves, let me tell you how we are organizing the cross-section. So we are organizing the cross-section as a function of these variables PT and delta T that I show you, that I defined before. And what we show you here is the yield, the differential yield of this cross-section, averaged over the angle of the momentum imbalance, the azimuthal angle of the momentum imbalance. And on the left, you have the collisions of virtual photon with transverse polarization with proton. And on the right, you have the collision of virtual photon with transverse polarization with nucleus. Okay? And you have three sets of curves. You have the CGC, the ITMD, and the TMD. Okay? These are for fixed PT and for fixed virtuality. But there is some features that I want you to get out of this plot. So first, you see that at large delta T, this means that the jets or the hadrons are not back-to-back anymore. At large delta T, you see a deviation between the blue points and the black dots representing the CGC. This is expected because the TMD factorization breaks precisely when this momentum imbalance is very large. It breaks for both. And if you include these kinematic corrections of the improved TMD, the agreement is much better between the CGC and the ITMD. It's even excellent at large momentum imbalance, even for these extreme regions. What is a little bit of a surprise, what was a little bit of a surprise at first, is that even at back-to-back configurations, where the momentum imbalance is very small, there are deviations from the CGC and the TMD. Recall that TMD and ITMD are indistinguishable at a small momentum imbalance. Okay? So these cannot be kinematic corrections. They have to be these genuine twist corrections, which were previously ignored in TMD, in the TMD framework. And they are enhanced, as you can see in this plot, for the nuclear collision. So more precisely, if you look at these ratio plots, you see that for the nucleus case, there is deviations in the exactly back-to-back when delta is very small, and they are more pronounced for the gold collisions. So let me show you how these deviations depend on Q square.
You have 3 minutes left.
Thanks, Olga. So I'll be very brief. This is the dependence on Q square. So now you see that if you decrease Q square, if you decrease the virtuality of the photon, these back-to-back deviations between TMD and CEC increase. They become more significant. And of course, they are more significant for the nuclear DIS than the proton DIS. And this may be a way to access and scan this genuine twist by studying it with the virtuality dependence. All right, very briefly, let me show you now the elliptic anisotropies. And same game as before, we have 3 different curves, CGC, ITMD, and TMD. You see large deviations between TMD and CGC at large delta, shown in the difference between the blue and the black dots. But you see that when you include the kinematic corrections, the agreement is much better. And the point here is that these azimuthal correlations in the TMD framework only come from the linearly polarized Weizsacker-Williams. But the ITMD itself includes azimuthal correlations between P and delta, and these have to be taken into account. And that's why you see the differences in the V2 between TMD and ITMD. Briefly, some results for V4 for the quadrangular anisotropy. This is completely absent in the TMD framework. And it was a bit unclear if this V4 came from the genuine twist or the kinematic twist. So it seems like a mixture of both. Kinematic twists, as shown in the red curves, leads to V4, but the genuine twists seem to suppress it a bit, as you can see between the difference between these red and black curves. Okay, so this is my summary. It looks like TMD framework works quite well for various range of kinematics when the collision is between virtual photon and a proton. The form of the ITMD is suitable for coupling with event generators. And I think Piotr is going to discuss some of this in his talk. If we want to extract this linearly polarized Weizsacker-Williams, one needs to account for these kinematic corrections because they can induce the correlations between P and delta. And this genuine twist can be hopefully accessed at the EIC in back-to-back configurations when one performs collisions with nuclei. Just let me flash my our outlook. So one would like to couple these results to hadrons and jets by coupling with fragmentation routines and hadronization routines, jet reconstruction. And of course, a natural step is to extend to NLO. And there is some work in progress with Paul Kaukal and Raju. We are pushing in this direction. Okay, thank you very much.
Farid, thank you very much for this very nice talk. We still have 2 minutes for questions or comments. If you have any questions, please go ahead.
Hi, can I have a question? I cannot raise my hand. It's Piotr speaking.
Go ahead, Piotr.
Very nice talk, Farid. Thank you. I have a question. Did you try to see how those genuine twists scale if you increase capital PT?
Yes, if you increase capital PT, they decrease as expected.
Yeah, so for instance, just roughly, because I saw you had like 2 GeV. For instance, if it's like, I don't know, 4 or 3, can you like roughly say what will happen to those?
They become very small. So if you are interested in moderate jets or hadrons, they become very small. So it will be a challenging measurement.
Okay, thank you.
But this is, I mean, this shows the power of the ITMD framework in this way, that it can reproduce quite well the full CGC.
Okay, thanks a lot.
We have another question from Fabio. Fabio, please go ahead.
Hi, Farid. I have a quick question. It wasn't clear to me what exactly goes into what you call CGC. You're evaluating the full quadrupole and without making any approximation of the momenta, right?
That's right. The only approximation we make is the Gaussian approximation, as you are very familiar with. And we use the RCBK for the dipole evolution, but we don't make any approximation. So it's numerically challenging to compute because you have the full quadrupole and then you have various kinds of convolutions. Yes.
Okay, just wanted to be clear. Thanks.
We have another question from Bovan. Bovan, please go ahead.
Hi, Farid. Very nice talk. I'm just trying to understand a little bit better here as following Fabio's question. So what if you increase PT again on the right-hand side of your plot for EA collision? So you show that there is a deviation between the CGC and the TMD for low delta T. What if you increase PT? I suspect that these 3 approach should agree again, right?
Indeed. If you increase PT or if you increase the virtuality sufficiently, this deviation will go away. Because these genuine twists go down with PT. I think in a previous slide. So here, I think there is a little bit of a lag. These genuine twists come in powers of QS over PT. So if you want to be sensitive to them, your PT should not be much larger than QS, right? And as we know, QS is 1 GeV for nucleus, maybe a little bit more, a little bit less. And and then if your PT is like 4 or 5, then it gets difficult. But of course, at the EIC, because you want the stuff to be forward, the PTs are not going to be super large, right? So
yeah, understand. Now I see. I guess in this case, in your previous plot, in the plot you showed, that's just because you in the case that PT equals to 2 GeV, the expansion that one usually does for TMD approach is not valid anymore.
Yes. Let me put it this way. The way you do the expansion, usually it's in coordinate space, right?
Right.
And assumes R much smaller than B. But there is another scale, right? 1 over QS.
Yeah.
Right. So that's how one can understand it as well.
Right. Thanks. Thanks a lot.
Well, Farid, thank you very much again for this very nice talk. I suggest we continue with the next talk. It will be Piotrek. Could you please share your slides?
Yes. Can you hear me, by the way?
Yes, we can hear you.
Okay, let me just.
So Again, you have 15 minutes. I will give you a heads up after 12.
Okay.
Because,
can you see my slides?
Yeah, we do.
And do you see my pointer?
Yes, we do.
Okay. Okay, thank you. So, so this talk is going to be, I think, complementary to the previous talk by Farid. So I'll be talking about Dijet production in the EIC kinematics, and more precisely, I'll be focusing on this Weizsacker-Williams gluon distribution a little bit. So fortunately, I don't have to talk too much about the introduction because it has been shown already a couple of times. But nevertheless, let me just spend 1 minute. So here you can see a formula for production of QQ bar pair within CGC formalism. And as Farid explained, you have this quadruple there. And this quadruple is related to this Weizsacker-Williams TMD gluon distribution. And actually, I'll be interested in unpolarized part of it. Which is called typically, but not always, FGG3 in terms of, let's say, TMD language, which I will talk about a bit later. And actually, and what is interesting about that is that this is the thing which is accessible in Dijet production. So we really have to tag both jets to access this distribution. Now, let me spend a little bit, just 1 minute on reminding those operator definitions of those TMD gluon distributions. So, so here we can see this very generic definition. So we have two gluon field operators, strength field operators. They are separated on the light cone and in the transverse direction because it's TMD gluon distribution. And we need those gauge links to make it gauge invariant. And those gauge links basically depend, I mean, because they are related to the resonation of collinear gluons in the hard part, so they depend on the color flow in the hard process. But what is nice about it is that basically you can build whatever those gauge links, I mean, whatever is the hard process, it's those gauge links are built from those two very basic objects, those two kind of staples, this future pointing staple, which is called U+, and past pointing staple U-. And as a result, you can build sort of a basis of operators or basis of TMD gluon distributions, which are listed here, all of them. They are in general quite complicated because they can contain loops, Wilson loops. It's when you glue together two staples. So for any process, that the TMD gluon distribution will be given as a linear combination of these. But what we are interested in, right, at first is the simplest objects that we have here. And those simplest objects is this one, this operator, which has one past pointing staple and the future pointing staple, which is related in the small x regime to the dipole operator. So let me go back to the dipole operator in CGC. And then we have this operator, which is even simpler. So it's it has two future pointing staples, U+, and when you choose a gauge, you can just get rid of this, and then it has a gluon number interpretation. This is even more basic than the dipole. However, it's you know, you need to have Dijet system to probe this gluon in that context. Okay, so sorry. Okay, now let me discuss what is the approach we want to, which we want to use to kind of study this Weizsacker-Williams small x TMD gluon distribution. So this is this ITMD approach, which Farid already mentioned. So the story is that the relation between TMD and CGC correlators has been established first in the back-to-back regime, but then we're sort of able to show that one can do better actually and separate the so-called kinematic twists and like genuine twists, which those genuine twists are related just to like harder MPIs in the sense that you have like higher twists, genuine operators. So you can separate those two and resum those kinematic twists into the hard factor. And still this correspondence between the TMD and CGC correlators would hold. However, there's one, so this is the approach, but there's one issue actually, and this issue is related to linearly polarized gluons. So in the cases that have been studied so far, I mean, at least we studied, those linearly polarized gluons, they did not enter the game. However, there are some cases where they do, for instance, like heavy quark production, and there's a very fresh paper by Tolga, Cyril, and Peter about that. So we don't have it, and we want to focus just on the Weizsacker-Williams gluon distribution, this unpolarized Weizsacker-Williams. So therefore, we are not taking this into account, this linearly polarized gluons. So therefore, we call this approach ITMD star. And we sort of, so what we will do, we want to have quite small Q squared, actually, not zero, but small, to get rid of that part, to sort of suppress this. So then the formula is very simple. It looks just like KT factorization, except we have this Weizsacker-Williams TMD gluon distribution. But what we want to do, we want to have the Sudakov resumation. So we want to go beyond just the naive leading order, let's say. And then the hard part is just built out of offshore matrix elements. And what is nice about that is that it can be implemented in Monte Carlo. So, all the calculations can be done in a very convenient way. So this study is complementary to some studies that are already out there. One sort of studies is full CGC. So this is what Farid discussed. And there is also the study by Zheng, Elke, and collaborators where they used MV model and the Sudakov in the back-to-back regime. So we kind of go beyond this back-to-back regime, and we're going to use a little bit different model for the gluon distribution and a little bit different observables. Okay, so now how to get this Weizsacker-Williams gluon distribution. First, our procedure is the following. So first we look at the dipole TMD gluon distribution, however, with very specific evolution equation. So I put this evolution equation in full glory here. So this first line is just the BFKL. I mean, there is this kinematic constraint put by hand in here, which is proven to work very nicely, actually. So this is just BFKL. And the last line is just the nonlinear term. Okay, so this is nonlinear equation of the BK type. But we have this additional DGLAP corrections. And so this equation is based on this Krichinsky-Martin-Stachta equation proposed a long time ago. So, and this can be fitted to deep inelastic scattering inclusive Hera data. It has been done already some time ago. And then for a nucleus, we just adjust this R parameter. And then having the dipole based on this equation, which we think it works better at larger X, then we can calculate the Weizsacker-Williams in the Gaussian approximation. And here's how we do this. It's just, just numerics, but we do include the proper Sudakov factor calculated some time ago. So this is how we get gluon distribution. And here is a plot which shows the result for that, for proton and for lead, for different choices of the scale. Well, so it's just a result, but maybe I just want to remind that this Weizsacker-Williams gluon distribution behaves very different at small KT than the dipole gluon distribution. So the dipole gluon distribution, you see this saturation pattern as sort of a moving bump, and then it drops down to zero, and Weizsacker-Williams behaves very differently. So, the hope is obviously that the Sudakov will not flash out the saturation effects with Weizsacker-Williams. This is one of the motivations for this study. Okay, now let me start discussing the results. So having this Weizsacker-Williams gluon distribution in the framework, which I discussed, we try to select some cuts. So here's what we do. We take 90 GeV as the energy, both for electron proton and for electron lead. Then we have Q squared, which starts as 1 GeV. Okay, but the jets, we cut jets at 3 GeV. So it's so it's small, kind of, as for jets, but one can do also hadrons. I mean, this is necessary to kind of focus on the small, reasonably small x. And then we started two types of rapidity cuts. One is the symmetric, from -4 to 4, and another one is asymmetric. And actually, I will be focusing on this asymmetric rapidity window. And the reason is that if we plot x of gluon, so x of gluon for digits is not Bjorken x, it's different, okay, first of all. So it's gluon x on the x-axis. And then here on the y-axis, I have just rapidity difference. It could be something else, but I just, this is what I picked up. And then if you look at the symmetric rapidity cut, you see it's like very broad. So you go really to higher x's of gluon, which we don't want to do, not yet, at least, not with this gluon distribution that we have right now. Whereas if you impose this asymmetric cut, you have this very nice focus on this smaller x, okay? So you can also see this when you plot just the correlation between the gluon x, which is on y-axis, and the Bjorken x here. So for asymmetric cut, you have this kind of nice correlation. But if you do symmetric, then you really go to higher x's of gluon, and the same if you increase the PT cut. Oh, sorry.
Peter, you have
yes?
3 minutes, okay?
Okay, very good. Okay, so now so this was our choice for the cuts, and now the observables. So we consider two types of observables. Both are based on azimuthal angle. So one is the azimuthal angle between the jet plane. So it's a azimuthal angle between the plane spanned by the jets and the electron, outgoing electron. Okay, this is one thing we can do. And we did calculation both in the bright frame and in the center of mass frame. And the main result is the black and red. Okay, so it's like full calculation with Sudakov. And then if you compare this to the calculation with no Sudakov, this blue and orange, you see very significant effect of that. But what is interesting, that this saturation effect is still there. It's like 15% with this choice of cuts, but it's there, and it's not destroyed by the Sudakov here. And now, one interesting thing here is that we also compare this to our older model for the Sudakov. These are those dashed lines. So this Sudakov model, it was very simple, but I think very reasonable thing is that just after generating Monte Carlo events, you can just reweight your events by assigning some survival probability based on the Sudakov. So, but then there is one restriction on that which you need to impose, and this was just that the total cross section does not change. It's like in Parton shower. Parton shower is unitary thing. Cross section does not change. So we did the same, and that's the result. So you see this kind of more proper Sudakov has different normalization. Okay, and another natural observable related to azimuthal angle is just the azimuthal angle between the jets. Okay. Here what we see is that it's very steep. This distribution is like very, very steep. So it's kind of hard to see the saturation effects for that observable. But there is but there's a big difference actually between the Sudakov scenario, full Sudakov scenario, and no Sudakov, or this older Sudakov model. And actually that's it. So let me I guess I have like a minute to summarize. So what we did, we first we calculated this unpolarized Weizsacker-Williams TMD gluon distribution with the proper perturbative Sudakov factor, but we used this dipole gluon distribution based on data with this Diglov improved evolution equation, and then we applied this to this ITMD approach with which does include the kinematic twists, and we studied those two observables which I just discussed. So it's a azimuthal angle between the plane spanned by the jets and the electron, and just the angle between the jets. And it seems that the first observable looks more sensitive to the saturation effects, and the Sudakov plays a very important role in both. And also, it seems that it could allow to distinguish between different Sudakov scenarios, because, as we know, there's always some non-perturbative input required. And obviously, the next step, as everyone says, is the full NLL computation. But we want to have something which can deal with that automatically in Monte Carlo. Okay, so that's it. Thank you very much. I'll be happy to answer any questions.
Thank you, Piotr. We have 2 minutes if there are questions, comments. Yeah, Farid, please go ahead.
Hi, Piotr. A very nice talk. So if I understand correctly, right, the Sudakov is more important when the jets are almost back to back, because one have this separation of scales.
Yes.
While the ITMD is more important for the other extreme, where delta is comparable to PT, correct?
Yes.
So they seem to work on different regions. Is there a clear interplay between the two, or are they kind of independent in some way?
Yeah. So thank you for that question. This is So there's one subtle point in that which I think I'll have time to discuss. However, so first of all, one can ask, because we sort of go beyond the derivation of the Sudakov, because it has been derived in the
exactly.
Right. However, if you look, at least for the IS, if you look at the diagrams in certain gauge which are involved in that calculation, they are, so I'm talking now about just when you neglect the genuine twists, okay, and you have, it's only a two-body contribution and the kinematic corrections, the diagrams are the same. It's just that the certain gauge, you do not have any additional Lipatov type diagrams there. So I think that this will hold still, and you can apply the Sudakov to that part.
Yes,
so that would be my answer.
My concern was that, as you said, Sudakov is formally NLO, and it was shown to have this form when the jets were back to back, right? In the paper by Bowen, Al, and Feng. So I was wondering if somehow the kinematic corrections could spoil that nice form, because you have a very nice form, right? You have the Sudakov part, which acts on the Weizsacker-Williams, and then you have the kinematic corrections, which only act in the Hard factor. So I wonder if something could spoil that nice factorization, but okay.
Yeah, I mean, I think this deserves more careful study, which we actually didn't do. We just kind of analyze this from this point, which I just said a minute ago. So I don't really know, but I think it should work for this, for just the kinematic twist. I think it should work the same. There is actually one thing which the question is, what about the region where KT is much bigger than the Hard scale? Let's say, how to deal with that? Whether one should kind of keep some sort of artificial constraint in that region, or just allow to Sudakov for Sudakov to suppress that region. But this, I think, I mean, that deserves a bigger discussion.
I see. Thanks.
Well, we have questions from Jamal and Bovan, but if they're not super urgent, I suggest to take it offline, that you can discuss maybe.
Okay? I just want to quickly chime in here, following up Farid's question. So basically, there is a kind of interplay between the Sudakov and the ITMD approach, because the Sudakov only matters when they are really, really back. The digests are really, really back. If you go away,
I can't hear you, Brian.
Oh, we cannot hear you. Hello, Bogan?
Sorry, we have issues with connection. We don't hear you, I guess.
Okay, yeah, and we are really running behind. So I suggest you discuss with Bogan after, like, offline. Okay. I'm
okay.
Sorry.
Thank you.
Okay, let's continue with the next speaker, which is the last speaker of the session, Andreas van Hameren. Andreas will talk about forward trijets production and saturation. So Andreas, it will be again 15 minutes. So I'll give you a heads up after 12. Please go ahead.
Okay, can you hear me?
Yes, we can hear you.
And the slides also visible? Okay, if you don't complain, I guess you can see it. So thank you for the opportunity to talk about this work that I did with my collaborators that will be mentioned, or their names will appear during the talk. And while we are at DIS, it is not DIS that I will be talking about. I will be talking about hadron-hadron, more precisely, hadron-hadron proton nucleus collisions. And the reason to study is to eventually to study the effect of saturation. And we in particular wanted to make the step to study saturation in, let's say, multi-jet events. And so the idea is to have a dense system like a nucleus with many low X partons and a dilute system with a few high X partons. And the kinematical configurations to look at then is forward jets, because the whole system is expected to be boosted into one hemisphere. And so we heard this already, that the proper way the proper theory to study saturation is the color glass condensate. But it is possible in certain limits to extract some nice factorized formulas from this color glass condensate that have roughly the shape like I showed down here. There was I think in 2011, there was for dijets, they extracted a formula which we call generalized TMD factorization. This was in a limit where the dijets are back to back. And there was a formula which involves, it was a hybrid formula. So there is one large X parton with a collinear PDF, and then there's the small X parton with some TMD and a hard cross section. And in this generalized TMD factorization, the jets were expected to be back to back. So this KT in the hard matrix element was 0 and only showing up in the TMDs. Now, what we did, we tried to make an interpolation of this formula with high energy factorization, where you allow for finite KT also in a hard matrix element. But the difference in the formula is then that in high energy factorization, you have only one TMD, right? So when I have here this sum over I, this is sum over TMDs and eventually color structures of the hard matrix element. And so originally this was as a kind of an interpolation. We came up with this formula. We know how to calculate these hard matrix elements, but then it was proven that you can extract this generalized, this improved TMD factorization from CGC, where you take into account this kinematic twist. And so what I'm going to talk about is generalization to more than two jets. I call it ITMD star because we are not able to have the full formula yet. And the problem is that it's called this so-called linearly polarized gluons. This is a contribution that is expected to show up. And what I mean by that, I show here, let's say, a formula that you would find if you extract some factorized formula from the CDG, where you have this matrix elements, the hard scattering, and this F and H, they represent something like TMDs. And what happens is that in this, we're talking about KT-dependent matrix elements. Okay, so this amplitude is like a let's say stick to gluons, a multi-gluon amplitude, but one of them is off-shell. It is space-like, it's not light-like. You can calculate this in a gauge invariant way, for example, by using a specific gauge, and then you indeed have to take into account only the usual Feynman graphs. You leave one of the gluons simply off-shell, but it must have a specific type of off-shellness. It must have a longitudinal component, not just KT. But then you can use this KT as the polarization of this off-shell gluon, and that thing will be gauge invariant. That's the correct object that you need, right? And as you see in this formula, that would correspond to this part. But you will see that in general, you will also need a part where you somehow terminate this off-shell gluon, not exactly by the KT, but you can, for example, write it like this, by a momentum that is orthogonal to KT. And it has been seen in other processes that are not just dijets. Very recently, this paper by Peter and collaborators. So while for dijets this disappears, for example, I think because F and H are identical, so you don't have this. But in general, it will be there. This is something we didn't solve yet. So I will just be talking about this piece that we know how to calculate, and it's manifestly gauge invariant. Now I want to show how you get this structure with these different TMDs for different color structures. And a nice way to see this is by using a specific color representation for multi-particle amplitude. So if you have a cross-section, like I wrote here, a cross-section formula for, let's say, KT factorization, where you have KT-dependent PDF, TMD, how you want to call it, collinear PDF, and there will be a matrix element, and you have to sum over everything, write colors helicity, and I write the sum over colors explicitly. And an elegant way to write it a bit more explicitly is by using this color flow decomposition or color flow representation, where you say each gluon from the color point of view becomes a quark-anti-quark pair. And then there is hidden inside the amplitudes, there are these 1/NC corrections to make sure that this quark-anti-quark pair is actually, from the color point of view, also a gluon. But you can write it then in very elegantly, this sum over colors in this way. And now, how you go from KT factorization to the formula to improved ITMD. So in ITMD factorization is you replace this TMD times matrix element by a matrix element where now the color sum is replaced by color correlation. So you don't have just the sum over i's and j's directly connected, but there is some correlator, complicated correlator, and this consists, of course, of some product of Wilson lines and the field operator squeezed in between the hadron states and Fourier transformed. And then the idea is that if you have more and more external particles, gluons, and anti-quark pairs, you will finally simply have more and more of these Wilson line operators in this object here. And in principle, that would be the general formula. Now, this looks still very complicated, but then, of course, there is this nice formula for the decomposition of this matrix element in terms of so-called, the amplitude in terms of partial amplitudes and a color factor. So you kind of exchange the sum over color into a sum over permutations. But if you put that in here, you see what happens. There are only these Kronecker deltas, so all these operators will be cross-connected by these deltas. And eventually what happens is that of all the possibilities that you could have with any number of legs, everything always collapses onto 10 possibilities. These are these possibilities that Piotr showed before. So the color sum is written in terms of a color matrix, usually in let's say in KT factorization, and now the matrix elements of this color matrix, they become TMD dependent, and it is always one out of these 10. Here they are again. It's exactly what Piotr showed. It's the dipole, and one of them is the Weizsacker-Williams, wasn't this one, I think. Okay. And then what did we do explicitly to do a calculation? So now what I said now is in principle exact in 1 over NC. If you want to do an explicit calculation, it becomes a bit still complicated if you would need 10 of them. So what you can do is make an approximation in 1 over NC, and then it's possible to start with a dipole distribution. So that's the one that you fit to data, etc., etc. And then you can extract the other ones in a mean field approximation. And so that is what he did for the dijets, and this happens to be also still enough for the trijets. And so I'm showing some plots for these TMDs then. And what is interesting here is, okay, the red one is the dipole, and this one you get from the nonlinear evolution decay equation, and this that is above a certain cut in KT. Below you have a power like fall off. And what is interesting here is then the other ones, the extra TMDs that you get, they don't have this fall off. This will be important in some plot that I show in a few slides. And what's also interesting, if you then compare TMDs that you get for a proton with those you get for say lead, then what you expect is that the lead TMD is smaller, in general true, but see the light color or the light blue one and the light red one is the lead. You see that for not so small values of X and large values of KT, the lead TMD can actually become larger than the proton. So the calculation that we did is, as I said, 3 forward jets. We did some rapidity window, typical jet definitions, scales choices, etc., etc. And then the interesting observables are angles between jets. And in particular, this delta phi 1, 2, 3 is the angle between the two hardest and the softest jet. This one is sensitive to the momentum imbalance. So if you would not have, let's say, if you would do a 3-level collinear calculation, this would just be a delta spike at delta phi is pi. And then we also consider, of course, the nuclear modification ratio. So you did the ratio of the lead, the cross sections, differential cross sections you get with lead divided by the ones you get with proton. And so in this first plot here on the left, I showed the nuclear modification ratio for ITMD in red and for high-energy factorization in blue. And here's again the picture that we saw before at when the jets, well, in this kind of view, we're not talking about digest, but when the system is almost back to back, you see a suppression. So that is the saturation. I mean, that's the idea, that this has to do with saturation. And then what is funny maybe is this fact that for the ITMD, you have the modification ratio becomes larger than 1, and that is, we suspect, coming from this thing that you saw before, that the lead for large values of KT and reasonable values of X becomes larger. The TMD becomes for the lead becomes larger for the proton.
Andreas, you have 2 more minutes.
2 more minutes. I'm almost finished, because the last thing that I wanted to say is about this plot here, where we have.
We're already running out of time. It's okay.
Sorry?
No, please go ahead. Go ahead.
Oh, okay. Here I show not a modification, the ratio, but the absolute value. So that it has then again this typical shape where you have a peak at pi, right, where the system is back to back, and a fall off for increasing momentum imbalance or small angles. And here you see that the ITMD calculation gives a bigger value, bigger absolute value than the high energy calculated value. And this is the effect of these TMDs. They don't fall off for small KTs. Only the dipole has this fall off, the other ones don't, and that gives this extra contribution. And that brings me to the summary. So I talked about small improved transverse momentum dependent factorization, and I introduced the calculation where you have more than 2 jets in the final state, 3 jets to be precise. And we see that also this kind of multi-jet systems that are interesting if you want to study saturation feasible to tracts. Okay, that's it. Thank you.
Thank you, Andreas. Okay, we have a couple of minutes to have discussions or questions. Bohan, go ahead.
Oh, hi, Andreas.
Hi.
Can you hear me?
Yeah, yes, I can hear.
Maybe you have mentioned already. I just wanted to confirm with you. So if you do trijet study, in the large NC limit, will you find the general kind of like universality or not? By universality, I mean that you only need the dipole and the quadrupole in this process.
So yes, so for in a large NC, you only need we only essentially need the dipole, and we extract the other ones. That's the other few that are also appearing. We can extract that in the mean field approximation.
Oh, okay. Good. Interesting. Thanks.
Well, if there are no more questions, let's thank Andreas again. I'm pretty sure everybody's hungry and we are a little bit off the time. So we will meet here at 6 in Central European time in about 20 minutes for the next WG2 session. Before I finish, I would like to ask all the speakers of the next session to upload their talks before the beginning of the talk. Thank you, the session. Thank you very much.